Okay, so thank you for inviting me for this talk, and gives me great pleasure in talking to you, the teachers, with utmost respect to all the teachers who are the fundamental building blocks of our society, who make the students to learn, particularly in the primary, secondary, and higher secondary education. You people are the initiators and mentors for knowledge for all our children. So first, let me congratulate and thank you for choosing the profession of teaching as your profession, and thank you for spreading the knowledge that you have acquired over several years, and the entire nation is indebted to all the teachers. So that said, I also take it as a privilege for me that I'm able to give some information about the satellite systems to you, so that in some minor way, if I can enhance your knowledge on these systems, which will be useful for you to teach the younger generation, it will be my greatest pleasure. So thank you very much for every one of the teachers who have joined this session and will be watching it either live now or later in the recorded program. Now, when I move on, before I talk about satellite systems, you must be knowing about what has been the achievement of the Indian space program over the last 6 decades. As of today, 121 satellites have been realized and launched by ISRO, and there have been 91 launch vehicle missions, which include 2 re-entry missions, and 424 satellites from 34 different countries have been launched by our launch vehicles. So as you can see, the entire ISRO, though, is responsible for the whole activity. The lead centers for all these activities are for the satellites URSC, for the launch vehicles VSSC, and the launch port at Sriharikota. These are the main centers. Of course, there are contributions in all the activities from all other ISRO centers also. Now, coming to satellite, satellites today touch every aspect of human life, as you might have already been aware. All kinds of satellites are touching the human lives in all possible aspects. For example, the satellite communication is the one which allows us today to seamlessly communicate either for personal communication, or either for entertainment, banking, or financial transaction, education. You name it. Every area, the satellite communication has revolutionized the communication technology, and India has been a major beneficiary of this, because satellite communication, the main advantage is in the wide reach and low cost. If you do the cost per capita, if you calculate the cost of communication through satellite, will be the lowest communication method. So the satellite communication is touching all our lives, which you all know. And similarly, Earth observation satellites also have been touching our lives, particularly related to the resource monitoring and the disaster management. The contribution from India's remote sensing satellites is enormous and unparalleled. I can recall when I was a school student in 1970s, whenever the cyclone season comes, it is a period of misery for the people, particularly in the East Coast zone, that is Tamil Nadu, Andhra Pradesh, Orissa, and Bengal. Every year, a few hundred people will be dead due to the effect of these seasonal cyclones that get formed in the Bay of Bengal. But today, hardly we see any loss of life due to these cyclones, and the damage to property and cattle also has been minimized. This is thanks to the environmental monitoring and disaster management aided by information provided by the remote sensing satellites. The tracking of the low pressure area and the cyclonic storms when they form in the ocean and continuously being tracked by ISRO satellites provide us sufficient warning when the landfall is going to happen, at what point, which allows the local government to take care of the rehabilitation, that is moving the people out of the danger zones prior to the event, and subsequently even the recovery and rehabilitation also is being aided, because the satellites allows the governments to assess the areas which require immediate attention, where the damage is more severe. These kind of information are now available to the administrators of the governments. That is why the Earth observation has played a major role in avoiding disasters. And the cartography satellites have been now utilized by almost every large companies, including to lay a railway track, to lay a gas pipeline, or to monitor a gas pipeline. These Earth observation satellites are providing yeoman service. It's a very important service the Earth observation satellites are doing to our nation, particularly our country. This is an important contribution. Coming to the navigation satellites, the impact of this in public life is not yet very significant, because the navigation satellites, when we started, were started mainly for the strategic users, and since we were late entrant to this navigation area, we did not get approval for providing the navigation service in the commonly used L1 band, which is used by other service providers like GPS. However, this year we had the first satellite which also provides the navigation solution in the L1 band, which is the commonly used navigation band, so that our navigation satellite, NAVIC, is also going to now provide services interoperably along with the GPS or other navigation service provider in 1 or 2 years, because we need to put in orbit at least 4 satellites to provide service from the first satellite only has been launched last month. So this is an area where immense potential is there. This is a very, very high value application domain, navigation satellites, which is very key for the aviation, marine, and surface transportation requirements. And many IoT based solutions for technological companies and even for households, the navigation satellite provided PNT solutions are going to enable these services. Presently, the services that are provided in the L5 and S band are being used by specific users who have to get a specific receiver realized for this. But shortly this is going to change. Any available commercially used handheld device also are now going to receive shortly our own navigation satellites, NAVIC services, which will going to revolutionize this sector in India also. Finally, the space science satellites, This is very important, not only from the science perspective, but it is also important from the point of view of outreach and uh, providing a platform for the student and youth community to feel proud and to inspire them and motivate them to take up the STEM education. The science, technology, engineering, and mathematics education is key in any society, particularly a society like India, where the population is so high, the available natural resources in this country are per capita, if you see, is not very high. Technology is the only solution which can make the lives of our people better. So to achieve that goal, it is essential that the students and youth should get motivated and inspired to study science and engineering and mathematics. This is what these space science satellites are doing. The what a Chandrayaan 2 did, or what a Mars orbiter mission did, uh, equivalent to that kind of interest in science and technology, it is very difficult to achieve it by any other means. So more than the actual science or technology that comes out of these missions, the the motivation it gives for the youth of this country is invaluable. So the satellite program, that is how, if I can summarize, for all these four verticals of satellite technology, it is very important in our Indian context, because as I mentioned, our country is multicultural, multilingual, multi-ethnic society, where if you travel by 100 or 200 kilometers, you will see completely different set of culture, language, and it requires multiple ways of reaching out to the people. So that is why the satellite has been seen as a viable tool by our visionary leaders like Professor Vikram Sarabhai, so that very large area of coverage, independent communication links, very quick reach, because instantly satellites allow us to reach to any part of the country instantly, and very cost effective. And the coverage over the entire Indian continental subcontinent is possible. This is the only means through which we can do this. That is why for our society, a satellite technology based application development is very important. Now, coming to the working of satellites, it's not very complicated. Basically, satellites are working basically on the Kepler's law of orbital motion and the Newton's law of physics and Newton's law of gravitation. These are the laws which govern the satellite working in orbit. As you being teachers, you are all familiar with the Kepler's law, Newton's law of physics forces, and Newton's law of universal gravitation. These are very important for understanding how a satellite works. Now, when you throw a projectile, any object, when you throw, it is called a projectile because it is traversing a path. And if the path becomes closed, that path is now called an orbit. So any object which orbits around another object is called a satellite of that primary object. So for example, Moon is the natural satellite of Earth, and whatever satellites we make and launch to the orbit are the artificial satellites. The satellite is kept in position by the balancing of the forces, the centripetal force vis-a-vis the gravitational force. The balance of these two forces is what is keeping the satellite in orbit. some basics about our planet Earth. The radius of Earth is about 6,000 kilometer average. This is the average radius. This is not same. Earth is not a perfect sphere. It is an oblong sphere. The average radius is 6,378 kilometers, and as we all know that it makes a rotation about its own axis once in 24 hours, and it makes a rotation about the sun every 365 days. That is how the day and the year are achieved. If you are looking at the speed in which the Earth is moving, these are all very fantastic speed. It is roughly 40,000 kilometers per second, or 460 meters per second is the velocity of Earth. Whereas you compare this with an aircraft which is flying at 800 kilometers per hour, it is roughly about 220 meters per second. So that gives us the scale of the speed in which the Earth is rotating. The factors that affect any object which is put in an orbit around another object, for example, the natural or the artificial satellite of Earth around Earth, or the varying gravitational field, because since Earth is not a uniform mass, the mass of the Earth is also varying radially as well as in the other direction also. There is a varying gravitational field. The effect coming from third and fourth body, that is the effect due to our moon's gravity, effects due to sun's gravity, and in a minor way the effects due to remaining planets in the solar system, all affect the orbit of an object which is put around Earth. And more closer to Earth, the atmospheric drag, though we say the atmosphere ceased to exist at about 100 kilometers altitude, the atmosphere still exists even up to say around 500, 600 kilometers. It is a tenuous atmosphere, very low density, still affects the orbiting satellite through the drag, which the drag of the atmosphere even at about 500 kilometers is not insignificant. And another important force which affects satellites in Earth orbit are the force applied by the solar radiation. Though sunlight is not a particle, okay, there is a particle wave duality is being attributed to light. Though we are not able to feel any force when sunlight falls on us. In the absence of all other forces, the force exerted, the solar radiation also exerts a force, especially on large surfaces when they are in space. This also affects the orbit of satellites around Earth, and of course, finally, the Earth's magnetic field also affect the Earth's satellite motion. Now, other important things to know about orbits around Earth is, if a satellite is orbiting around Earth in the plane of our equator, it is called an equatorial orbit, and the orbit is said to have an inclination of 0. If it is going in the clockwise or anti-clockwise direction, they are called prograde or retrograde. If an orbit which is at 90 degrees, close to 90 degrees over the poles, if it goes, these are called polar orbits. Now there are special orbits within low Earth polar orbits also, which are called sun synchronous orbit. When any object which is orbiting Earth, the orbit also precesses around Earth, and when the Earth's rotation and the precession of the orbit match, then the orbit is supposed to be called a sun synchronous orbit. When the orbit precession matches with the Earth's rotation, what happens is the position of sun with respect to the equatorial crossing point remains same every orbit. It means whenever the satellite crosses the Earth, the illumination condition at the equator remains exactly same as any orbit. The only change that happens is due to the change in the declination of the sun, which is the seasonal variation of plus minus 23.5. So this is a very important orbit for Earth observation. The polar sun synchronous orbit, typically the sun synchronous orbit is a function of inclination and the orbit altitude. The inclination is around 90 degrees, close to 90 degrees. That is why this is called polar sun synchronous orbit. So as I just now mentioned, the polar sun synchronous orbit is an important orbit for Earth observation. Similarly, there is another orbit called geosynchronous orbit, which is at the height of close to 36,000 kilometers above the Earth's surface. At this altitude, the orbital rotation of the satellite is nearly very closely matching with the Earth's self-rotation, which means an object, a satellite placed in this geosynchronous orbit will move along with the Earth's rotation, meaning that it will see the same part of the Earth throughout its life. Every orbit, every day, that is, if the period of that satellite will be equal to 1 day, so the rotation of the Earth about its own axis and the rotation of the satellite about Earth's axis will match, and it will appear for the user on ground that that satellite is stationary with respect to the user's position on ground. That is why the name geosynchronous orbit. Most communication satellites in the past were placed only in the geosynchronous orbit, taking advantage of this apparent fixed position with respect to a point on the Earth. Of course, nowadays, in addition to this geosynchronous orbit, the communication satellites have now moved to even low Earth orbits. These are handled in a slightly different way, but the conventional way of communication satellites, where continuously you want to service a location on ground with one satellite, geosynchronous orbit is the right orbit. Now, having discussed about the basics of the Earth orbit and different types of orbits for satellites, we'll discuss about satellite building itself. Now, what are the requirements that have to be taken care of while building a satellite? Those things I have now identified them as the space demands, because any object which you put in space are going to work in a very hostile space environment. When I say hostile, there are multiple reasons. The space is very cold. It is close to minus 271 degrees centigrade. In the absence of any other source of heating, the temperature of the space is minus 271 degree centigrade. So it is going to be very cold and there is no air. So it is vacuum, completely vacuum, hard vacuum is there. And when you are putting an object in that space, when it is exposed to sunlight, depending upon the surface property of the object, the sunlight is going to heat it very high. If the surface property of the material is adversely designed, then sun can heat an object which is in the Earth's orbit to temperatures in excess of 250-300 degrees centigrade. So you have thermally a very hostile environment. The temperature can vary from very high values, say roughly between plus 300 to minus 300 degrees centigrade in high vacuum. If this is not sufficient, we have even more hostile environment, because the energy coming from the sun, the sunlight contains harmful UV radiation. We at Earth are protected by the thick atmosphere of about 100 kilometer height above the Earth's surface, which scatters the ultra or absorbs the energy coming from the ultraviolet radiation. It does not allow the ultraviolet radiation to reach the Earth's surface. Whereas in space, the ultraviolet radiation is nothing to stop it, so it is going to interact with the satellite. Similarly, space is full of lot of charged particles. That is very high energy electrons, protons, alpha particles like this, and there are some small number of heavy ions. Large number of charged particles are there. These are all going to be very damaging to the material which we are putting in space. So this is a very hostile environment. And if you are putting any service in space, the service has to be autonomous and continuous, because users demand breakless, that is with uninterrupted service, and autonomous. The satellite is not accessible to you all the time. It is not visible to you, but it has to work round the clock 365 days a year. So only way to make is everything on the satellite has to work autonomously, and if there are any failures, deviations happening, satellite has to, in most cases, identify itself there is a problem and reconfigure itself so that service is not affected. To achieve all these conditions for the service conditions to be met, very specialized expertise and skill sets in multiple disciplines are required to make a satellite, and very high-tech manufacturing and testing capabilities are required, and the design tools required are also very sophisticated, and exclusive tools are required. And the last but the most important thing is very high quality and reliability. When I say quality and reliability, reliability is a quality over a period. Quality is a very high quality at the instant. Yes, it is high quality, but it has to be the same high quality for a very long period under different operating conditions. That is reliability. So these are the fundamental demands of anything which is put in space. Now, what are the other challenges involved? Because of this long life of satellites in orbit, user demands keep changing because the technology gets updated very frequently. Moore's law, you would have heard. The technology keeps updating very fast. The user demands changes. So the satellites, what we are putting in space, which work for 10-15 years, we need to anticipate what is going to be the technology roadmap in different areas and make the satellite either agnostic to those changes or adaptable for those changes. And this multidisciplinary linkages demands that it is not an expertise from either only a mechanical expert or an electronics expert or a software expert independently do this is not possible. That all disciplines of science and engineering, the people have to work together to realize a satellite. And the unwritten or the not so obvious knowledge is in the mission planning, operation and execution, which is the inherent knowledge, which is never taught anywhere, which is never written down, which is never documented, but this is by experience the knowledge comes. That is the mission planning, operation and execution knowledge. And the risk and uncertainty involved in these systems make this very difficult for taking large amount of risk in introducing new technology. That is why we need to make a very informed assessment about which are the risks and uncertainties associated with any new technology or new component while inducting into the satellite, because even the smallest component, a failure in an on-orbit satellite is going to result in possibly a total loss of a satellite, which is a very expensive item. And similarly, since it is being a satellite which has to be launched through a rocket, There are constraints related to mass and volume, and you cannot put the satellite at whatever time you want for specific applications. There are requirements related to the launch windows and opportunities. There are like this a very large number of considerations while building the satellite. Now, the different parts of the satellite, if you can see on the right hand side, you see what is shown as the payload system. This is the purpose of the satellite. Any satellite is made to provide a service. That is, the service is the purpose of the satellite, and that service is provided by providing some data or giving some communication or doing imaging. These activities are carried out by payload systems. These are the functional application elements. The payload systems are related to the different application which I mentioned: communication, remote sensing, navigation, like that. These are the ones which are the most important elements which are going into the satellite. But it is like the people living in a house. The houses are built for people to live. So depending upon the different type of people and their requirement, the house has to be made adaptable for the requirements of the user. That is, as per the requirement of the payload, the house needs to be built. The house is, in the case of a satellite, is the bus system, which involves large number of systems. There is a structure, there is a thermal management system, there are going to be certain mechanisms which are going to do certain openings, rotations, like that. There is going to be a power system, because every system which is in a satellite requires power to operate. We require telemetry, telecommand and tracking, which is like speaking, hearing and following, navigating. For that we require digital and RF systems, and we also require a onboard computer, which is the brain of the satellite. So a large number of systems are involved in any satellite. This picture shows you the disassembled view, that is the exploded view of a typical satellite. This is just an example. The shape is not necessarily this has to be like this only. It can be any shape. But these are the principal elements. There are a large number of elements which are going. You have a structural member, which is like building our physical structure of our house, the walls, roofs, like that. There are going to be thermal control system. It's like having fans and air conditioning at home. There are going to be power system, batteries, solar panels, which is like getting power supply and UPS from our service providers. Similarly, as I mentioned, there have to be some communication system, which is like talking to us and telling about its health, satellite's health, and receiving a command from ground and executing that command. Like this, a number of systems are there. There are a number of sensors which are there on board the satellite, which act like eyes and ears of the satellite to know about the satellite's surroundings. So on the right top side, you can see a satellite. When it is finished, it is ready for launch. It will be more or less in this kind of shape. So as I mentioned, I'm not going to go through the entire this one. As I mentioned, the structure is like our house, our home, walls and roof. Thermal subsystem is like our fans and heaters and air conditioners. Propulsion subsystem is like having our car or a two-wheeler, which allows us to move. Like that, the satellite also needs to be moved around to keep it operational. Similarly, there are mechanisms. These are like opening your hand, rotating your fist, like that. Many things are done by us. Like that, in the satellite also, the payloads and other systems required to be rotated, moved, opened. These are done by the mechanism systems. As I mentioned, the power system is like our electricity and UPS at homes. The control system is the one. It is like the parents at our home who control everything at home and make sure that there are nothing going out of control and everything is done properly. This is the brain of the satellite, which makes sure that the satellite behaves properly. The communication system, as I mentioned, is like our hearing and speech, which will tell it's about its health and obey the commands given from the ground. There are large amount of data generated on board the satellite. So this data needs to be processed and downlinked to the ground for use. For that, data handling systems are there. And to be aware about the surroundings of the satellite, we require the sensor systems, which tells about where we are in space. And there are inertial systems which allows the satellite to keep balance, like when we are going in merry-go-round, how we feel vertigo, like that satellite also will feel a vertigo. The inertial systems are the one which stabilizes that rotation and make the satellite feel stable. And as I mentioned, the mission management is one which is the intangible knowledge, which is never taught in any college, which is learnt through experience of building and operating satellites. And the satellite is a complex entity. So different people, very large number of different entities make different parts of the satellite, and they are assembled and tested together by a specialist team of people who do the satellite assembly, integration, and testing. And of course, the whole thing is monitored and controlled by the reliability and the quality assurance people, which ensures that the required processes are followed, tests are carried out, and the protocols are followed. Now, coming to payload, there are first let us talk about the Earth observation remote sensing payload. How it you can see the principle is like that. Sun light is incident on our Earth's surface. It is getting reflected back. See, like in a dark room, you cannot see anything. Like that, without sun, we are not it is not possible to see anything on the ground. In the visible domain, like with our eyes, we cannot see. But if I put a night vision camera, I can see even without light. Exactly the same way, remote sensing is done, either by illuminating the object which you want to image from space while sun is present, or you you look at the infrared image, or you illuminate from the satellite itself. So these are the three different ways of doing remote sensing. So this is done throughout the entire electromagnetic spectrum, starting from microwaves up to X-rays. Even gamma rays are used for imaging the deep space galaxies and how the universe has followed. Every part of the electromagnetic spectrum is used, and as in this picture you can see, the different part of the electromagnetic spectrum allows us to look at different aspects of the objects which we are trying to remote sense. So as I mentioned, what is illuminated by sun, that is called the optical remote sensing. What is illuminated by the satellite using a microwave, using a radio frequency wave, is called microwave remote sensing. When you are looking at a microwave which is emitted by a source on ground, that is a passive remote sensing, passive microwave remote sensing or radiometry. Whereas when it is illuminated by a microwave which is emitted by the satellite and gets reflected back from the Earth, it is the active remote sensing. And for any remote sensing, there are multiple resolution involved. Spatial resolution, it is about what is the smallest size of the object we can look at. A spectral resolution, which tells I can see blue light, red light, yellow light. What color you are able to see in terms of wavelength? Color is a property of the wavelength in the visible region, but whereas in the non-visible part of the electromagnetic spectrum, it is the spectral resolution. Similarly, the radiometric resolution, if I am looking at as a temperature infrared imagery, what is the minimum temperature differential I am able to identify? That is the radiometric resolution. Similarly, temporal resolution is the resolution. What is the shortest time gap? What is the time required for processing the data between one image to the next image? The temporal resolution. Like this, a large number of resolutions are involved. Microwave imaging is a very, very important technology which allows us to see through the cloud and the night duration of any object, which requires a very elaborate processing arrangement on ground and on the satellite. But this is a very, very important remote sensing technology which allows us day or night or the shine or rain, we are able to image. So the same thing what I mentioned is put in pictorially here. We'll move on to the next. The microwave imaging is basically the radar imaging. In radar, there is a concept which is used in satellites, which utilizes the very, very high speed of motion of the satellite to an advantage. That is called the synthetic aperture geometry. If you can, if I can imagine an antenna which is kept in space is repeatedly sending microwave pulses. Between one pulse to the second pulse, the satellite has moved in its position. This is equivalent to the antenna on the satellite having that much area. That is, instead of having a very large antenna, by making use of the motion of the satellite or the antenna in the space from one instant to other instant, we are apparently increasing the aperture size of our radar. That is called the synthetic aperture radar, which is the revolutionary technology which allows very, very high resolution imaging from space. And to scan the image on ground, there are multiple methods, like you can scan an entire area, or you can like a still photograph you can take, or you can like a broom, you can move from one direction to other direction, or you can like a weaver's machine, you can one width and that can keep on moving, the push broom. Like that, multiple ways of imaging Earth are there. Coming to communication, we have the microwave, and nowadays even optical communication are being contemplated. We are using mainly in the microwave imaging from L band. But very few people use the lower frequencies than that. From L band up to V band are currently being used, and they are used for different services. So what band for what service in what regime is controlled by an international body called ITU, that is International Telecommunication Union, so that there is some order and some regulation, so that the one operator, one service does not affect other. That is how this communication through microwave is getting regulated throughout the world. And in communication, there are multiple methods called the broadcast service, which is like our television broadcast coming from satellite to ground, like our DTH. We have mobile services, like there are satellite phone service providers, not in India, it is not yet come, it is there elsewhere in the world, where through satellite a user can make a telephone conversation from one user to another user. That is called mobile satellite services. not only telephone, including there are multimedia services are available like this. That multimedia services are available even in India through our GSAT-6 satellite. Coming to navigation, as I mentioned, the navigation provides us the position and time information, which allows us to come up with an enormous number of applications. The most important equipment on board a navigation satellite is the atomic clock. Recently, the latest navigation satellite launched by us, NVS-01, includes indigenously designed and realized atomic clock on board, realized by our colleagues in the Space Application Center in Ahmedabad. It's a great achievement. Like today, every mobile user is dependent on the navigation services provided, and most of our apps which work in our mobile, like your Zomato or Swiggy or any other such apps, everybody is depending upon both the navigation and the geopositioning data that are provided by software. This is a very large application potential area, with including like how aircraft can be very safely landed. For that, this Gagan scheme has been worked out, where we are providing better than 1 meter accuracy for an aircraft while landing on airports, so that the accidents at the time of landing and takeoff are avoided. Finally, coming to the space science domain, as I mentioned, science is important, and exploration is the nature of human being. It is to explore things and to know the unknown is the fundamental quality of the human being. That is the reason the science satellites exploring Earth as well as beyond is an important part of the space science. But there are also other aspects related to technology, philosophy, and more practical aspects like economic benefit. From all points of view, space science is very important, because most of the applications today, the gadgets and items we use, have come out of the research that has been carried out towards the space science, like our the pressure cooker, microwave oven, like this. A large number of items have been, which are today day-to-day used by us, have come through the space research. India's own science and interplanetary missions, we have had so far 4 dedicated science missions. The Chandrayaan-1 launched in 2008, the Mars orbiter in 2013, the AstroSat 2015, which is very important satellite, which is a mini Hubble Space Telescope. As it has provided such a large amount of data, very huge amount of scientific research has happened using AstroSat data. And of course, the Chandrayaan-2 orbiter, for last 4 years, it has been providing outstanding science from Moon. In a short while, a large number of other science missions are planned. Within this year itself, we are expecting 3 more science missions of ISRO to be launched. And as we get these satellites launched, we'll talk more about that. And the latest all around the world is to shrink the satellite and achieve similar or better performance through these small satellites. So though the large satellites even today are having their own requirement for specific applications, many of the non-critical applications can be realized through small satellites, as has been shown by the new space explosion around the world. Large number of small satellites are being launched all around the world, and it's only a matter of time in India also we are going to see a large number of small satellites getting launched. So this is the benefit of the small satellites, which of course allows the deployment or testing of a small application, a revolutionary application in a short time with minimum expense. Even some failures can be tolerated. That is the main USP of small satellites. Even further, the world is moving towards nano satellites, where satellites of less than 10 kilogram weight are now being thought of to provide services which were once provided by satellites of the size of 500 kilograms or 1000 kilograms. So as like the mobile and computer technology area, satellite technology area also is getting shrunk by the revolution in the semiconductor and other technology areas, where the same functionalities or better functionalities are achieved through smaller devices. So very exciting time ahead for the space technology area. As I mentioned earlier, irrespective of the other commercial and technological benefit, as a person who has been working in this domain for last 37 years, the most important benefit I see in the space technology, satellite technology, is related to the STEM education. Science, technology, engineering, and mathematics are key. These are without the in these 4 areas, trust and a large number of youth taking to this area, the society cannot hope. Our Indian society cannot hope to match or to better the advanced rich countries. This is the only way we can bridge the gap between the rich countries and developing countries like India. So to all the teachers who are today listening to this talk, it's a very pivotal role all of you are playing, particularly the science and mathematics teachers. It will be a great privilege for us that whatever today I spoke for about 50 minutes, if it has given you some information which will help you tomorrow in giving more knowledge and making more number of students get interested in the STEM education, all our effort is paying dividend. And the goal for us is invent, innovate, and implement. Thank you very much for your time and patience. Wish you all the very best. Thank you.